Alrighty, so the last topic, major topic of the unit is the relationship between models, theories, and laws. And we're going to throw the word hypothesis in there as well. Okay? You have a package in front of you. I'm going to try to go through the whole thing. It's going to be one of those days where you're going to have to sit and listen to me. Thanks, man. I'll try to be as entertaining as possible this semester. Okay? What I want you to do before we start is across the top right here, I want you to write, I've got it like from top to bottom, and you can write it sideways. I want you to write hypothesis, arrow, theory, law. That's going to be the main structure of today's little topic. Okay? So right across the top there, hypothesis, theory, and law. We're going to investigate that, keep coming back to it. Don't put it underneath because you need that room for some answers. Don't put it underneath. You're going to need that for some answers. Don't put it underneath. Put it across the top because you're going to need space for answers. How many people believe, hands up right now, hypotheses become theories and then are proven to become laws? Leighton says, really, only a few hands. It's okay to be wrong. I've already made a mistake once today. Okay, interesting. A lot of people not sure. Not sure. Okay, so what we're going to do is we're going to try to activate some prior knowledge here, figure out what you already know. So I want you to take, there's 8 questions. I picked a particular TED lesson today to show you, atomic theory. Okay? Probably all that stuff you sort of knew, right? Okay, from, but pretty much kindergarten right on up, right? Certainly early chemistry, they talk about the development of the atomic model, okay, or the atomic theory. So what I want you to do is I want you to answer those 8 questions. I'm going to give you like 10 minutes. Okay? You can work with someone. You can come up with a joint answer, the two of you. I don't care. I just want you to sort of get what you know out of your head and onto paper. Okay? And so at 9:16, we're going to go through those answers. You may be surprised. I guarantee you will be making some mistakes. That's my job as track. Okay. Go ahead. Tell me what you know already. Okay. So, remember, this is what you think. I am not giving answers. Yes. Don't worry. I'll tell you the truth. Just not yet. Okay, put those devices away. You need to listen. You really need to listen this period, you guys. Okay? Unfortunately, there's not going to be a lot of practice. There's not going to be rulers. There's not going to be protractors, any of that stuff. Unfortunately, this is a you have to listen and think. Okay, so those phones need to go away. Okay, so just quickly, let's go through. I want to hear what you already think, sort of get an agreement on the class, and then I'll tell you the truth. So, number 1, what is a scientific model? Give an example. Who's got an example of a scientific model? Late. Bohr diagram. Perfect. When did you learn that? Grade 10, right? With me, I think, right? Grade 9 or 10 science. The Bohr diagram. It's a model. A model is something that, how would you describe it? Shows what? Shows what's happening. Is it something that, like, how come you have to show what's happening? How come you can't just see what's happening? Like in the Bohr model, too small, right? The Bohr model is a way of describing something that we can't see because it's too darn small. Here's another example of a model. Why is this a model? Because it's too darn big, right? It's a physical representation of something that we can't see. That was the truth. Physical representation, something we can't see, or something that we can't, or doesn't exist physically, right? It's a way of physical description. Okay, scientific law. Who's got an example of a scientific law? What's not the scientific law?
Law of gravity.
Law of gravity. What is the law of gravity? Uh-oh.
Whatever goes up comes down.
Whatever goes up must come down, okay? That's certainly a rule, right? One of these days, one of these years, I would love to be able to go over here to my tennis ball collection, which I always pull out for this particular demonstration, and I would love to throw the ball up, and it would just stay up there. Man, that'd be cool. But I can't do it. Okay? Because what goes up must come down. A scientific law. Does everyone sort of agree with that? Okay, now, not listening, man. Seriously. So important today. It is, okay? Big marks on the test, it's got to be listening. Okay? What is a scientific theory? A little harder. Josh? No? Scientific theory. Zach? Okay, can you give me an example, someone? It's pretty easy. Examples are easy because it's like the theory of, or theory of evolution. Explain, what is the theory of evolution? In like a one-sentence kind of format. How organisms evolve, right? Move from one to another based on what their needs were, kind of thing. Is there a lot to the theory of evolution? Yes, you can write a book on it, right? Does everyone more or less in the world agree with the theory of evolution? Everyone more or less. When I don't mean like 100% every single person. I mean, is it widely accepted by the scientific community? Maybe that's a better way to say it. Yes? Generally accepted. There are still some people that don't believe, that's true, but generally accepted by the scientific community. Maybe not the general public. Okay. Now, number 4. How do we prove scientific theories?
By experimenting.
Experimenting. Yep, every time I throw the ball up, it comes down.
If you tell them I'm not going to go through the roof and it won't come down.
Good point, Fred. Okay, so there are certain exceptions to the rule. Yeah, absolutely. Okay, or if it was windy enough, right? Or what have you, right? By doing experiments, is that what they did with the atomic model, the atomic theory? Who was the guy that put through the gold foil? You remember the name? I heard Rutherford. Rutherford's gold foil experiment. He was trying to figure out if there was a nucleus to the atom or whether it was completely solid.
Remember that PDF problem was having?
Yeah.
Not saying like the required element is missing or all that.
Doesn't like
That's every computer, it's just a PDF.
I'll come with secretary. Number 5. I'm going to ask Hannah because I know she's got the answer. Do you believe in atoms? Good. There was someone that, it was Sandy, I convinced her to write it down. She wasn't sure if she believed in atoms or not. Who doesn't believe in atoms? Nobody. Yes, I know. Because atoms don't believe in Josh. Most people believe in atoms. How come? Why? Because teachers right from kindergarten pretty much have been telling you atoms make up everything, right? Have you ever seen an atom? You see lots of them every day, but you've never seen, yeah, no jokes, you've never seen a single one. You can see the look on his face. Okay? You've never seen one, and yet we all believe in them. Believe in atoms? I'm looking at you, Stan.
Yeah.
Yeah? Okay, let's check. Now, how are science and art similar and different? Now, you probably never, ever, ever thought about this. I don't even know why it's up there, but I like talking about it. Who wants to tell me, how are science, let's do the easy one first. How are science and art different? Alyssa? Don't know? Jessica, how are science and art different? There's one sort of glaring, kind of obvious answer. Nolan? You're always right. You've been right 5 times now. No, Brennan's happy, yeah. No, this isn't one of them? Okay. Sean? Come on, you guys know you're scared. Because you're afraid of being wrong, and that's okay. Don't be afraid of being wrong. How are science and art different? When you do it,
Hold on.
when you do a math question or a science question, generally there is a correct answer, is there not? In the back of the book. Art, you go down, like, do some art with Mr. Miller, and is there a right answer?
Yes.
Well, he's looking for certain things, right? But generally, there's no right answer, right? Okay, so now that we know that, how are science and art similar? This I guarantee you won't get. And I shouldn't say that, but I've never had a student come up with it. How are science and art similar? If I take you to a museum of fine art, and you look at all these paintings and you go, yeah, boring, 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 don't care, don't get it, whatever, right? Why? Because, and even myself, I don't know much about art to appreciate fine art, right? It could be paint by numbers from someone's garage sale or a $2 million painting. I don't know the difference. The Canadian government, about, I don't know how many years ago, a long time ago, there was this great big canvas about the size of the wall. It was completely red. They paid $2 million for it.
Completely red?
It was completely red. One, like, primer and red. That's it.
And you become an artist.
Yeah, exactly. Like, I mean, everyone's got that in their house. It's called walls. $2 million. Okay, what about science? Can you appreciate fine science? Do you need to know something about art to appreciate fine art? Yes. Do you need to know something about science to appreciate fine science? Yes, you do. Okay, so science and art do have a similarity, which is one reason why we teach science in class, in school, so that you can appreciate it and understand what's going on and get the jokes in the Big Bang Theory. Number 7. Some astronomers say the universe is expanding. Some say it's shrinking, and others say that it remains at constant size or it's static. How can these scientists arrive at completely different conclusions when they look at the same evidence, exactly the same numbers, same data, they all come up with different conclusions? No, they're not stupid people. There's a reason for it.
They have different prescriptions.
They have different what?
Prescriptions.
What do you mean by prescriptions? No, that's not it. That's a good one. I appreciate a fine joke. That's a good one. When a scientist is trying to prove something, remember when we watched the video about the 2, 4, 8, right? Remember that one where and they couldn't get it, right? It was they were trying to find something that proved their theory instead of trying to find something that disproved it, right? So when a scientist says that they come in with a personal belief that the universe is expanding, they're going to look for data that proves it. They're not going to look for data that disproves it. It's just human nature. Okay? So you have to be very careful with experiments. Like Leighton said, that's how you prove theories. You don't want to try to prove your theory true. You really want to try to prove it's not true. The problem is how do you prove something not true? Does doing it once prove it? No. But if you can make it not work, then you can disprove it. It's hard. Okay? It's hard. I'll just sort of leave that alone for the time being. Can scientific theories change? Everyone should have got this answer. Can scientific theories change? Resounding correct answer, absolutely 100% is yes. I gave you an example this morning. The atomic theory, right? The atomic model. Sometimes they call it model, sometimes they call it theory, right? The model is sort of like the diagram, the theory is sort of all the talking that goes around. Okay, so yes, scientific theories can change. Now I'm going to show you a video. The guy is he's kind of a little odd, and he kind of talks kind of soft, okay? So you're going to have to listen very carefully, but he makes a very important point. So I'm going to put my speaker down here on my microphone, try to listen carefully. When someone says, oh, it's only a theory, they're in fact showing their ignorance. And when I say ignorance, I mean their lack of understanding, okay? I don't want to say stupidity, ignorance, their lack of understanding, okay? Theories are backed up by data, explanations, and generally are accepted by the scientific community. There's different types of theories, and we'll get to that in a short bit. But theories do not become laws, never will become laws, aren't supposed to become laws. In fact, they are two completely separate things. You couldn't really understand, you couldn't really hear him. What he was saying was that the law is like Leighton said, theory of gravity. Different theory of gravity, right? But Leighton said, what goes up must come down. That's the law. It must happen, right? You try it. I guarantee you it'll come down, right? It's the law. A good thing the law wasn't when you throw something up and you catch it. Because we would have disproved that law. Theories do not become laws. I can't stress that enough. Okay? Theories do not become laws. Theories explain why when the ball goes up, it comes down. Why does the ball come down? Because of gravity, right? And to be honest, we don't really understand why the Earth pulls on the ball, but that's the theory. And it's not just, oh, it's only a theory that it's going to come down. No, it comes down every single time, guaranteed. 100%. Okay? 100%. Now, again, who cares? I'm going to show you another video. This guy, this is from a few years back, was running for the President of the United States. Not Al Gore. His name is Rick Perry. He's a governor. I don't remember what state. He's talking about climate change. Listen to what he has to say. What did he say? He gave that little look too, right? What did he say? He said, well, it's only a theory. What's he implying, huh? That we're going to wait for the day for some scientists to prove it. Will that day ever come? No. It will never, ever, ever be proven. 97% of the world's scientists believe it. Is that enough? That is up for debate. But what's not up for debate is that 97% believe it, based on evidence, okay? And when politicians come along and say, and it doesn't have to be American politicians, it can be politicians anywhere in the world, when politicians come out that aren't scientists and say, well, it's just a theory, guess what? They were texting in grade 11 physics class. Or call you out, right? But if I hear you guys say it's just a theory, I'm going to be mad. There are good theories, documented theories, and there are theories that still need some work. Theory is an explanation. Okay? All right. Can we flip the page now? Do you sort of get where I'm going here? Is it kind of making some sense? Okay? I guarantee I'm going to ask you on the test. I'm going to ask you a question that is designed to get at the point. Do you understand if theories become laws? Hopefully you're listening. Hopefully you get it. Okay? I'm going to do one reading here, and then I'm going to be quiet because I can see that I'm losing it. Okay, let's read the first one. Science is more than just a collection of facts and observations. Models, laws, theories, and evidence all play an important role in understanding the nature of science. A scientific model is, get your highlighter out, pencil, put a star beside it, Jimmy crack corn, I don't care. A scientific model is a conceptual representation that stands for and helps explain other things. It's a way of explaining. Conceptual representation, either an idea in your head that stands for and helps explain other things. It could be physical, like a globe or a board diagram, or it could be imagined in my brain, or it could be mathematical, it could be numbers and formulas. That could be a model too. In science, we develop models that have explanatory and predictive powers, like the model of the universe, and we test these models in the world around us. If our model predicts our observations, we accept the model as a valid description of our world. However, if our model encounters discrepant events, there's a new word for you, discrepant. It's kind of even hard to say, discrepant. Anyone know what discrepant means? A discrepant event? This would be a discrepant event. If I toss the ball up, it stayed there. That would be a discrepant event because it would go against all of our beliefs. Okay? It's something that shouldn't happen. Discrepant event. And fails to provide adequate explanations, we begin to modify our model or search for an entirely different model. Did the atomic model change over time? Yes. How come? It encountered discrepant events. They found out things that didn't match the model, and so they had to change the model. Did this model change over time?
Yeah.
Sure did. What did they once believe? That it was flat. We encountered discrepant events. We went around the globe. Right? Right? We went around the globe. Hard to believe, but there's still people out there that believe the world is flat.
But yeah, it actually was, and he fell off the edge.
You would fall off the edge. Can we prove it?
Yeah.
Absolutely. It's not a theory. It never was a theory. It's a model. Okay? The theory explains why it's round. Why? The theories explain the why. Okay? It's a fact. A good example of a scientific model is the model of the solar system. At one time, it was thought that the sun revolved around the Earth, and this geocentric model of the universe was considered to be a true representation for many centuries. The model encountered a discrepant event when the retrograde motion of the planets did not exactly fit the episegments of the geocentric model. I'm not even speaking English anymore. Okay? If you watch the planets, if you are an astronomer, you'll see that the planets, as they go through the sky overnight, will do this, and they have this little loop-de-loop, this retrograde motion. And some guy, Johannes Kepler was his name, came up with these crazy mathematical equations to match them. And they weren't quite perfect because it wasn't true. Not happening. He tried to put his theories, his beliefs on top of something that the model was wrong. Okay? Who was the guy that said, no, the Earth's not at the center, the sun's at the center? Anyone know? Who's the guy? Danish, I think. Come on, you know the name. When I say it, you're going to go, oh, yeah, right. Copernicus? No? Yeah, see, I knew you knew. Someone knew. Nikolai Copernicus, right? He's the guy that said, no, the sun's at the center. When they put the sun at the center, all of these things stopped happening, and we didn't need the crazy mathematical ones. They adjusted the model when they found a discrepant event. Okay? A new model, the Copernican sun-centered model, provided a simple explanation of the movement of the planets, and it predicted the phases on Venus. You know how the moon has like full moon, quarter moon, half moon, all that? Same thing is true on Venus, you just can't see it because it's so far away. So it predicted that, and then when we got powerful telescopes, oh, hey, it's right. So we found more evidence to the model to add to the theory. Observations can be used to test models, both externally or by thought experiments, as we rethink and apply our model to new and sometimes discrepant situations. Our observations can lead us to identify regularities and patterns in nature. We call these regularities and patterns scientific laws. Is it bold in your sheet? Just barely. Highlight it, star it, underline it, do something. A scientific law is a regularity or pattern. Something that always happens. Every spring, the Maple Leafs do not win the Stanley Cup. That is a law. 1 year it will be disproved. Okay? It's something that always happens. When you throw the tennis ball up, it always comes down. For example, a few simple scientific laws would be what goes up must come down. We can also deduce laws given a certain set of conditions. For example, if light is a wave, we can geometrically show blah, 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 who cares? Snell's law, Ohm's law, Charles' law, Newton's laws. You can tell something is a law because it usually has the word law in it. Newton's laws, they tell you what happens. Okay? They tell you what happens. Which isn't that hard. Yeah, I maybe. Contrary to popular belief, laws are not absolute but are often constrained to certain conditions. Ohm's law is valid only for some materials, and our pressure laws are constrained by temperatures. Even Newton's laws are only valid in their initial frames of reference. Okay, so all laws have exceptions. Let's say that. Okay, here's the next highlight, paragraph, right here. Scientific theories form explanatory systems for phenomena and their corresponding laws, and may include presuppositions, models, facts, and laws. That's a mouthful. Scientific theories form explanatory systems. They explain why something's happening. Climate change theories are explaining why something is happening. Okay? For example, Einstein's theories presuppose that the speed of light is constant in all frames of reference. In Einstein's world, Newton's laws, such as F equals ma, hold only for objects that are moving much more slowly than the speed of light. We must be very careful how we use the term theory. That's the whole point of this whole day. So you're not being a stupid politician and stand up there going, totally theory. Because if you do that, and I'm in the audience, I'm going to stand up and I'm going to call you on it. I guarantee it. That is a theory? Okay, well, that's not explaining why. Especially if you've been in my class and if I hear you using the word, it's just a theory. In everyday usage, the word theory often refers to an idea that's not proven. Regular guy on the street, politicians that don't know better, so on, use the word theory when it means something that isn't proven. That's not the scientific explanation. It's not the scientific definition. Okay? It's partially true that some theories, like many cosmological theories, are speculative ideas and based on little evidence. I'm going to draw something right away. Additionally, children often hold simple or naive theories about why things float or why the sky is blue. Hypotheses or proposed solutions are often speculative, and we often seek to build support for them through predictions and observations. However, other theories, like theories of radiation, metabolism, chemical bonding, have considerable evidential support. So there's lots of evidence to support them. It is impossible to prove our theories for every possible case, but robust theories explain a great deal, and we sometimes literally bet our lives on them. Therefore, scientific theories lie along a spectrum from speculative hypothesis to robust explanatory systems. I'll explain all that in a second. In science education, we often use early models of theories that are adequate for a less sophisticated understanding of a scientific concept. For example, Bohr's model of the atom explains all the phenomena that one might examine in an introductory chemistry program. More progressive theories require a more extensive backup. We teach you Bohr's model because it makes sense for grade 10, 11, to 12. When you get to grade 12 chemistry, they're going to start moving away from Bohr's model because it doesn't work anymore. It's a simple model, okay? At the bottom of that last page or at the top of the next one, I don't care where you do it, I want you to write these two words. Speculative, and then I want you to write an arrow, and robust. Speculative and robust. Okay? These are the types of theories. What's a spectrum? It's like a sliding scale. Okay? When theories start off, they generally start off as being speculative. There's a lot of questions. The answers aren't there. It's not fully understood. But as the experiments are done and as more data is gathered, they become more and more robust. The theory of evolution is quite robust. It's universally accepted in the scientific community. Okay? There's lots of data to support it. Climate change started out as a speculative theory and is moving towards robust. It is not just a theory. It is almost a robust theory. It's just some people that don't believe it. Unfortunately, they're the ones that control the money. Okay? This is something you need to know. I will ask you, what is the difference between speculative and robust? Speculative is still a guess, not a lot of data, still not widely accepted. Robust theories, accepted, lots of data. For all intents and purposes, they've been proved. There's that word. For all intents and purposes, they've been proved. Are they still up for debate? Absolutely, right? But generally, widely accepted. They don't just become one day all of a sudden, okay, we declare it a law. Doesn't work that way. Okay, last page, and then I'll be quiet. I know I've been really pushing the boundaries. You're getting all antsy, right? I get it. I warned you ahead of time. I'm going to try not to do this every day. While it's important that our understanding of the nature of science is embedded in the context, the world is rational and can be understood, we can never know if we have achieved the most rational explanation. In science, the truth is elusive, but our beliefs must extend far beyond individual opinions. Key point there, our beliefs must extend far beyond individual opinions. Does Governor Rick Perry have an opinion? His opinion is that climate change hasn't been proved, and we shouldn't spend money on it because it hasn't been proved yet. He's catering to the people that want to make profit. He's not catering to the scientists. Sorry, I'm letting my own personal beliefs get in the way there a little bit. Or not get all the worked out about it. In science, we insist on an evidential argument. You can't dispute the evidence. Okay, I'm going to quickly run through this last one here and then I'll go. One of the main questions scientists are concerned with the relationship between theory and evidence. It's not unusual in science education to make a knowledge claim in the form of I know that. You know what? I'm not even going to bother with this. I'm not even going to bother reading it. Waste of time. What are the things you need to know? I'm going to just summarize here. I'll give you 2 minutes. What are the things you need to know? Go back and look at the highlights. What did we highlight? First thing was what a model was, right? Okay, so make sure that's highlighted. Should be first paragraph what a model is. You should know that. You should be able to give me an example of a scientific model. There's a few there in paragraph 2. Okay? Then we get into laws. Laws actually do what? They just tell you what happens. When you throw the tennis ball up, it comes down. It's the law. It's what happens. Okay? Then it gets into theories. And it talks about how theories are explanations for laws. Okay, and then at the bottom there, we got into this speculative and robust. Those are the highlights. Okay, I'll be quiet now. I'm going to hand back vector golf. If you haven't handed vector golf to me, you're going to have to do another one, because if I hand back the answers, I know what happens. So, if you are Guadalupe or Josh or Leighton or Madam Mustafa or Nolan, and you haven't handed it to me, I need it now. Like, you got 1 minute to get it to me, or I'm going to give you another one to do.